Alright, so what do we got going here now? Well, the next thing in this section, in section 4.2, I keep forgetting what section we're in, what does f double prime at x tell us? Well, I'm trying to think how much detail I want to go into here. Well, let's think about here. We know that f prime at x, several things we know about it. One is that it's the slope of the tangent line. We also know that we learned that it's a rate of change. And this is the one we're going to focus on here, rate of change here for a second. So it's the rate at which y value changes versus the x value. So I'm focusing on this one here so we can get a little bit of understanding of what the second derivative tells us. So f double prime at x here, this is equal to, well, we know this is just, I'm going to write it a little bit weird here, this is just the derivative of the first derivative. So this is still, since it's a derivative is a rate of change of the y value versus the x value. So, but the y value in this case here is my first derivative. So the second derivative is equal to the rate of change of the slopes of tangent lines versus x. Now let's maybe look at a picture here to get a little bit maybe more understanding here of this. And my axes here are going to be kind of ugly here. If I need to get better graphs, I'll actually take time to draw them better. So let's just look at kind of a parabola kind of shape here. And let's look at a couple tangent lines here. So if I look at this first one to the left here, I'll label this one here 1, has positive slope. And then if I look at number 2 here, which I'll put right here, this has negative slope. And if I look at here, number 3, 3 also has negative slope. But it's larger in magnitude than number 2. And when we say larger in magnitude, what we're referring to is we're just looking at the absolute value. And the reason we say larger in magnitude as opposed to larger or smaller is because you can get into trouble because -5 is a smaller number than -3. But sometimes you think of, well, wait, -5 is bigger. No, it's not. It's smaller. But if you look at the magnitude, the absolute value, well, it's larger in magnitude. So that's why we say that sometimes. But what I want to point out here is if I kept drawing tangent lines from left to right, the slope of those tangent lines keeps going down because I start here with a positive slope as a tangent line at number 1, and then I moved to the right and I had a negative slope, which means I've gone down in value. And then I kept moving to the right even more, which means I kept going negative even more, which means I have even a further smaller value, or so it's even more negative, and so it keeps going down. And so this actually tells me how the slopes are changing. But then if we look back at this shape again here, I'm just going to draw it without the axes. This is something that we actually have probably heard of before, and since we're not in class, it's kind of hard for me to ask a question of you guys to say this. But a shape like this we've often referred to as something that we call concave down. And concave down, well, the reason we are saying concave down, I mean, it's bent down. Yes, the sides are bent down, but really what is it indicating? That the slopes of the tangent lines are always decreasing. So that's what the second derivative tells us here. So second derivative gives information on concavity. Great. So we've learned what it is there. Now let's talk about concavity. First off, let's just look at some examples here. These are all examples that I've just drawn of concave up. These are all examples of concave down. And then you can absolutely have no concavity, but these are kind of straight lines. So no concavity for straight lines. And we can kind of maybe already guess what's going to happen here. The nice thing for us is it follows very much like our first derivative did, is that if f double prime at x is greater than 0, you might guess that this would relate to concave up, and you'd be correct. F double prime at x being less than 0 would be concave down. And then of course the last one would be f double prime at x equaling 0, which this would be no concavity. And I'll put in here, we're not going to spend a lot of time talking about this, but this is something that's a possible inflection point. And some of you might know what inflection points are already. That's great. If not, we'll talk about them a little bit later on, either in this video or another video. So no concavity is when the second derivative is equal to 0, and it's a possible inflection point. So one thing we can do here is we can then find intervals of concave up and concave down, just like we did for increasing and decreasing. So let's look at a quick example, a relatively straightforward one to start with. Okay, so find the intervals of concave up and down for f at x equals 2x cubed minus 5x squared plus 10x plus 1. Now what you're going to see here is that this is almost identical to the problem that we did with increasing and decreasing. The difference is instead of using the first derivative, we're going to be using the second derivative. So let's go ahead and look at that. So we need to get to the second derivative. Of course, we need to take my first derivative. And this function should be pretty straightforward for us to take a first derivative of. We get 6x squared minus 10x plus 10. Now I have to be extra careful, right, because I don't have you guys with me right now to double check all of my silly arithmetic mistakes, so I have to be extra careful. F double prime at x then, well, that would just be 12x minus 10. So I need the second derivative. This is going to give me information about concavity. And so what do I do here? Well, I'm just going to first off do a similar thing before. Is they're not called critical numbers, but I'm going to find when is this second derivative equal to 0, because that's where I have no concavity. And so I'd have 0 equals 12x minus 10. And so then you have 10 is equal to 12x. And of course, x is equal to 10 over 12, which is 5 over 6. Now, we're going to do the same thing as we did before here. I'm going to draw a number line, but I'm going to just put off to the side here. I'm looking at the second derivative. So when you do these sign diagrams, you have to determine whether you are dealing with the first derivative or whether you're dealing with the second derivative. And because I'm talking about concavity, I'm dealing with the second derivative. So I'm going to put my only point where I'm 0, which is 5/6. And then I'm going to just do the exact same thing we've done on all the other problems here. And I'm going to go ahead and write the second derivative down again here so I don't lose it. I'm going to pick points in these corresponding intervals that I can test in my second derivative. So in the left one, hopefully it becomes obvious. I think I should test x equals 0, because that would be very easy to do. Now again, we're plugging this into the second derivative. So this would be 12 times 0 minus 10, which is negative 10. So again, the key thing isn't so much the 10, it's the fact that it's negative. And I'm not going to scroll back up, but if you're taking notes, we know that negative means it's concave down, which I think is great because that just kind of goes with my intuition, negative meaning down. So I know that I'm concave down here. Sometimes people like to draw the shape of concave down. That's fine. I'll go ahead and do it right here. The issue is you don't know for certain that it looks exactly like that shape, because remember there was 3 shapes that we had drawn for concave down. But this is really just to help keep our thoughts straight. It's not really an answer here. Alright, so then of course the other interval we have to test, I think an obvious number to test here would be to test x equals 1. So f double prime at 1 would equal 12 times 1 minus 10, which we can see, and I'm going to emphasize here, is positive 2. So that means we are concave up. So my intervals of concavity here. Now, this is one thing you want to make sure to do is answer the question. If you just have the sign diagram with no intervals, you're going to lose some points because it's asking for the intervals. So I'm concave up, and I'm concave up from 5/6 to infinity. And then I'm concave down from negative infinity to 5/6. Alright, now we could do some more examples of concavity, but they're exactly all the same here. You just have to find the second derivative of this. What I'd like to do here in the next video, which will be the last video for class on Wednesday, is to actually talk about how to use the second derivative to determine whether we have relative extrema. I'll be honest, we probably won't do too much with these here as far as finding intervals of concavity. It's not something we typically are interested in, but the second derivative is still useful to us.